So, we have looked at DQN, right. So, that is deep Q networks. So, now let us look at a few more recent tricks that people have tried with value function based methods before we move on to another category of learning algorithms, right. So, the first thing that we will look at today is the extension of double Q learning to the function approximation setup, right. So, if you remember, we talked about the maximization bias, right. So, we talked about the maximization bias where because you are using the same Q function for finding the max and also for actually estimating the values, right. So, the same Q function for max and estimating the values, you kind of tend to overestimate the value function while you are learning, right. So, if you remember, you had learning curves that went like that as opposed to going like this, right. So, that is something that we had when we looked at the maximization bias, right, and address that with Q learning, double Q learning, right. So, the idea here was that we will use two Q functions, Q1 and Q2, right. So, you find which is the max action according to one function, but you use the target according to another Q function, right. So, the actual value you take from another Q function, while the maximizing action you take according to one Q function. So, the idea is that you will not overestimate the same action's value under both Q1 and Q2, and therefore, you kind of reduce the effect of the maximization bias. So, this is what we looked at. Okay. So, how will you extend this idea of double Q learning to the deep Q learning setup, right. So, we call this double DQN, or as you can guess, it is called DQN, right. So, for the DQN setup, so what we are doing, we are now adding a replay memory and we are adding a target network, right. So, the target network is a time delayed copy of your Q network, if you remember, right. So, now the Q network is a neural network. So, obviously, so we have to now think about the Q function, right. So, now how do we do this? Do we add two more networks just like we did in the double Q learning case, right. So, we could add one for the online network and one for the target network to prevent overestimation. Do we really need to do that? Because we have a target and we have the freeze target, right. So, we have the target network and we also have the network that is used for learning. Do we need to use two targets? I am sorry, two networks, additional networks for each of these, or do you just leave the target network as it is and use one more network for the Q estimator, right. So, do you now learn three networks, right. So, the target, Q1, Q2, is that how you do it, or is there a clever way of doing it? Since you are already now having two Q networks, is there a clever way of doing this Q estimates, right. So, in fact, we can just use these two networks that we already have, right, and treat them like Q1, Q2. You are already using one network for the target and another for the estimation, right. So, now instead of finding the max according to the target, you can find the max according to the estimation network, but use the Q according to target or vice versa, right. Okay, so, the target is used for estimating the value and the online network is used for selecting the action. So, that is basically how we kind of extend this to the DDQN, right. So, basically if you remember, theta t minus is the parameters of my target network, right. This is the frozen target network. So, this is my parameters of my target network, and then theta t is the parameters of the network that I am currently learning, right. Theta t is the parameters of the networks I am currently learning. T minus is the target network, the one that I have already learned maybe 1000 iterations ago, frozen it, and now I am using that as my target, right. So, you remember why we are using this target network, so that we take care of the moving target problem, right. So, this is frozen and therefore, this is moving at a much slower pace than the online network that is changing, right. So, theta t is the online network parameter, theta t minus is the target network parameter. So, what does this expression give you, right, this whole expression. So, this one says you find the maximizing action according to your current network, and this says you update, you take the value of this maximizing action according to the target network, right. So, you do not use the target network itself for doing this. Earlier, the way we were doing it in the original DQN discussion that we had in the previous lecture, this also would have been theta minus, right. now it is theta t, and so that is on the online. So, this is basically you are getting the effect of the double Q learning by taking the max action according to one Q function, which is the current Q function, but taking the value of the target according to target, right. So, earlier this is what we had here, right. So, you took the maximizing action from one Q function, but you took the value from another Q function. So, the Q2 was the target for Q1. So, you can think of it that way. Now, the target network is a target for this, but we do not have to do the second update. So, we do not have to do this update because the target network anyway is getting updated only infrequently. So, we can keep it as it is. So, that is it, right. Putting these things together, so the double DQN step will go like this for us, right. So, this argmax will compute according to one function, right, which we call the current Q network is used for the max, and the target network calculates the Q value of taking their action in that state, right. So, that is basically it, and we can just do this. And for updating the target network, right, so we can do two things. So, the first one that we did, if you remember from the original Q learning thing, so was that after every 100 steps or every 1000 steps, we copy the weights of the Q network to the target network and then continue updating the Q network, right. So, that is what we did, right. So, the Q function continues to get updated every time step with a batch from the replay buffer, while the target network gets a copy of this every 1000 steps or so. Okay. So, that is how we do it. That is the first way of doing it. The second way of doing it is called Polyak averaging, where so we want to update theta t, right. So, we look at what is the current theta and some small fraction of the current theta we add to the theta t network, theta prime network. So, this is basically minus, right. So, this is the way we have been thinking about it. This is basically theta minus, and that is the current theta. So, I am going to say, instead of copying theta over to theta minus every 1000 steps, I am going to copy a very small fraction of theta over to theta minus in every step. Okay. So, where this tau is a much smaller number, so that allows my theta minus to change at a much slower rate, right. Theta minus changes at a much slower rate than theta. Right. So, theta will be changing at some alpha times something, right. So, it will be changing at a rate of alpha. So, I can take tau to be much smaller than alpha, and then I keep adding the tau times theta to theta minus, and so it will slowly drift, and so I can still use it as a target, because the target is changing much slower than my actual Q function. Okay. That makes sense. So, that is double DQN or DDQN or deep double Q learning, however you want. But the thing is, luckily all of this comes out to be DDQN for us. So, we saw a simple trick by which we can address the maximization bias, right. But given that we are now looking at larger and larger problems, right, there are other kinds of optimizations that we can do. So, one simple architecture which I personally am a big fan of, and I think it's a lot of good things can come from this, is this whole thing called dueling DQN, right. So, with the dueling architecture, it's a slight misnomer. There is really no dual that really happens here, but the idea here is to say that, hey, in many instances when we are solving large problems, right, in many instances, right, there is no big difference in the action values, right. When you are talking about small grid worlds and things like that, if going right is optimal and not going up, right, but then instead of going right, if you go up and then you come down and then you go right, you might cause, if the whole trajectory is only 10 steps long, and if you take 3 extra steps, right, you might cause a lot of change in the value function, right. The trajectory itself is only 10 steps long, and you take 3 extra steps, you can cause a big change in the value function. But the trajectory is, hundreds of steps long, and you get a lot of rewards along the way, and then you make like a small misstep, right, it really does not make a big difference, right, you can always correct it. So, here is an example from this Atari game called Enduro. It is a car racing game, and the goal is that you have a car here, right. So, you can see the car at the bottom of the screen, and there is a road that is curving ahead of you, and there are multiple other vehicles in the road, right. and so your goal is to make sure that you drive as fast as you can on this road without running into any of the vehicles or running off the road, right? You can't run off the road either, right? So in some cases, where the the complete road is clear, right? There are no real vehicles here. There is one vehicle far away in the horizon. There is a gradual curve and so on and so forth. It is not very crucial whether you go left, whether you steer left or whether you steer right, right? It is not very crucial. You can go left or right, but you can immediately adjust, right? So you go left, immediately turn right, or you go right, immediately turn left. So it doesn't matter which way you go, right? There is really no big change in the action values, right? Right? There is no real big change in the action values. What really changes is the value of the state itself, right? So if you are in the middle of the road, it's good, but if you are in the corner of the road, it's bad, right? So it's good to come back to the middle of the road. So it's only those kinds of the state changes are more important for the value function differences than the action changes itself, right? So if I try to learn just the Q function directly, I'll be trying to make a lot of unnecessary distinctions in states that don't need it. But then I can't completely say I'll go only with the value function, because there are states which will need the Q function. I need to be able to distinguish between the various actions, right? So for example, here I am driving, that's my car, right? You can see the car here, right? And then there are other vehicles in the road. So it's very important for me to make sure that I'm not moving in the wrong direction, because even a small wrong move can cause me to crash immediately into another vehicle, right? So I really have to worry about I really have to worry about the immediate action I'm going to take, right? So it's an important component, right? Right. So here I wanted to point out to these red activations, right? So the red activations are essentially those parts of the input. There's some way of determining this. If you have already looked at this in the deep learning class, great. Otherwise, you don't have to worry about it, how we do it, right? But the basic idea here is whichever things lights up in red here are the ones my neural network is currently using for computing the value, right? These are the parts of the inputs that are important in computing the value. So this looks at the value of the state, right? This in some sense looks at the value of the action. I'll explain what advantage is in a minute, but this looks at some sense the value of the action, and this looks at the value of the state, right? So this is something on the value of the action, right? And you can see that in the example that I explained to you earlier, right? So the value network actually is looking at some things in the input to make a computation, right? Well, the action network is not looking at anything. I mean, basically, there is no distinguishing features there in the action network, right? In the input that will allow the action network to make any changes. Therefore, it is not paying attention to anything in the input, right? While here, the value network is looking at a little bit attention to the score, but a lot of attention to the horizon, because you really need to know how far away the horizon is and the vehicles in the horizon, things like so. That's more important, and therefore the value network is paying attention to that. On the other hand, if you come to this situation, right, the value network does pay attention to the horizon, right, but also is paying a little bit of attention to the cars nearby and of course to the score. But the action network, right, is actually paying attention to vehicles now, right, because it's important for it to know what are the vehicles nearby so that it can make distinctions between the different actions, the steering actions, accelerate and so on and so forth, right. So that's basically the difference. So even if I'm setting up this thing to learn the value of the state and the value of the actions, you can see that the action thing doesn't really know what to learn here, right. So let me talk to you about a specific decomposition of the Q function that we are going to look at, right. So we're going to define something called as the advantage function, right. Let me make some room for myself, and I'm going to talk about something called the advantage function. So what is the advantage function? See, the advantage function as comma a, right. Unfortunately, advantage is called a. So as comma a is basically the advantage of taking action a in state yes is basically equal to v of s minus q of s comma a. So, what does it mean? So, that is a current policy. So, let us make this, it's be conditioned on the policy, right. So, A pi s comma A is the advantage that you will get by taking action A in state S and then following policy pi thereafter, right. So, what does it mean? So, V pi of S is the current expected value by following policy pi from state S, right, and Q pi s comma A is what? The value that I will get by following, first taking action A in state S and then following pi thereafter. Now, this should be seared into your head by now, right. So, V pi of S is the value that I will get, or the expected return I get by starting by following pi from state S, right. Q pi is first I take action A and then I follow policy pi, right. So, A pi is the relative improvement in value that I am going to get by taking action A over behaving according to pi, okay. Remember, Q pi does not give me quite that relative advantage, right. So, I am just using the relative advantage here, right. So, one thing to note is, if A is better than the current policy, by taking A, if I can behave better than the current policy, then the advantage would be positive. If by taking A, I can't behave better than the current policy, the advantage will be negative. It's not, I mean, so as with the reward function, right, we have positive reward and negative reward. You could have positive advantage and negative advantage with the advantage function, okay. Right. So, the advantage function basically tells you how much improvement you can get over the current policy pi by picking a different action. So, this is essentially, this network is modeling the advantage function, and here it says, hey, look, I do not care what action you take, you are not going to get a significant advantage, because there is nothing in the input that is going to tell me if there is an advantage or not. So, it is not paying attention to anything, but here it basically says that, hey, for computing the advantage, I need to look at this, okay. So, before I move on to show you something else, let me ask you this question, right. Let us say that I want to look at the optimal advantage, right. So, this is basically what is the advantage I get if I take action A and behave optimally thereafter, right. First in state S I take action A, after that I behave optimally. Instead of pi, now I have star, that means I have to behave according to the optimal function, right. What can you tell me about the advantage function? What will be the maximum value of this advantage function? Right, because by definition, we already remember, we started off by saying V star of S should be equal to max over A Q star of S comma A, right. So, A star S comma A, the maximum value can only be 0 for A star S comma A. For some A pi S comma A, the advantage can be positive. For A star, the maximum advantage you get is 0, and for any action that is not an optimal action in that state S, the advantage will be negative, okay, because V star of S will have a higher value than Q star S comma A for some A that is not a optimal action in state S, okay. So, that is just a small thing to remember, right. So, now having said that, how do you write your Q function in terms of your value function advantage? It is basically Q of S A is V of S minus A of S comma A, correct? Right, my Q function is just the value function minus the advantage, right, obvious, just little bit of a math, right. So, now what we will do with the dueling DQN architecture is that instead of learning the Q function directly, I will learn separately the V function and the advantage function. I will have two networks, one will learn the V, one will learn the advantage, and then I will combine them, right. I will take the output of the V, I will take the output of the A, subtract it, and that I will get a Q, and I will use that Q value to pick my actions, right, and I will use that Q value for updation and everything, right. And after that, back propagation will take over, I will change all the entire network, but I will only use Q learning still, right. I am going to use Q learning, but the way I construct the Q function is by first having a network that predicts the V, another network that predicts the A, combine those using some kind of a fixed function that will give me the Q value, right. Then I will then I will pick actions according to this Q value, be epsilon greedy, softmax, whatever is my fancy way of picking actions, I pick that, I perform the action, get the feedback, compute the TD error, find the gradient, and then update the entire network, both the V and the A networks. I'll update by back propagating the error, right. So that's basically the idea here, and the reason is in many cases the A itself, right, will be uniformly 0, because all actions are equally good, right. So for most of these actions A will be 0. So for many cases I don't really have to worry about learning A, all I need to do is worry about learning the V function, right. So in such cases I can learn with the fewer samples of such states, right, states like this, and therefore the learning can be faster, the learning can be a little bit more robust, because I am trying to learn an average of the state value as well as the action value. So sometimes this allows me to learn in a more robust fashion, right. So this allows me to, kind of learn with fewer samples, and we will see this in practice that this actually helps a lot, right. One thing to remember is that, so we need to make sure that the output follows this form, right. So we have something called an aggregation layer, which will combine the output of V and A, and it is fixed. The aggregation layer's weights don't change, right. The aggregation layer's weights are fixed, but you will back propagate the error through the aggregation layer, right. So there is a problem. So remember that when we actually try to, finally derive the Q function, right. So we have to make sure that the final form of the function is like this always, right. So you have the V network and you have the A network, and you're going to combine them and get the Q value, right. And this Q function has to be, aggregated the same way, and when we are back propagating the error, this portion of the network doesn't change, right. So this layer, which is called as an aggregation layer, right, and this portion of the network will not change. Okay. But there is an issue here, because we are learning both the V function and the A function separately, right. Just saying that Q is equal to V plus A might make it non-identifiable, as they call it. That's because there are many different A functions and V functions that can actually satisfy this, right. So I can basically scale the value by some constant, and then scale the advantage also by a similar constant, and therefore this might not work, right. So to make sure that I am always identifiable. So one of the points that I can use for this identifiability is, for example, remember what do we have? So we have to make sure that the advantage, right. So as you go to the optimal way of behaving, right. So the advantage function should go to 0, right. I mean, so the maximum of the advantage function should go to 0. So one way of making sure you get this whole thing centered is to say that Q equal to V plus A minus max of A. Right. So what this means is, this expression, whatever be the function I am learning for A, this expression will go to 0. My max of this expression will go to 0, and therefore my V will now have to scale itself down, so that Q of S comma the best action will be the value of the state, right. Only then I can get the right combination, right. So I can do it this way, right? But the problem with doing it this way is what? So first thing, let me reiterate what we have done, right. So if I just have V plus A, then I can scale up my V and A by any amount, right, and then I'll still get my, right. So if V goes up, A will go down, or A goes up, V goes down. So these things can be scaled, right, arbitrarily, so that my Q function is correct, because remember, at the end of the day I am training on Q learning, right. I am only having a target for the Q value. So finally my Q prediction will be correct, but what fraction is given by V and what fraction is given by A is up to chance, right, depending on the initial values and other things. So a whole bunch of craziness can happen. I don't want that, right. I mean, there is a specific definition for what V should be and a specific definition for what A should be, and I want to see that that definition is maintained, right. So what I can do is I can try to enforce the V and the Q to be the same for the best action. That's the kind of what you would expect, right. So you are going to be taking the best action most of the time. So my Q of, I mean, S comma the best action in that state should be the value function for that state, right. So I want to make sure that that condition is maintained. So that way then this arbitrary scaling cannot happen, right. So one way of ensuring that is, instead of just saying V plus A is my Q function, I will adjust the A by the maximum advantage I have learned. So even if my network is scaling up the advantage, arbitrarily, right, because I am kind of normalizing it by subtracting the maximum value, for the best action this expression will become 0 for the best action. Therefore, Q of the best action should be equal to V. So that kind of gets enforced, and therefore the system becomes identifiable. So this is one way of making sure that you are learning the right advantage and the value function. So even though you're just using one Q error, right. But the problem with this expression is what? I have a max here. Now that makes it hard for me to do the propagation through max. I can't do the back prop through a max, right. So I would like to have something that is simpler. Therefore, we actually use the average advantage, right. For A is the number of actions, right. So we kind of use the average advantage. So this allows me to ground the advantage to a baseline, right. That's what essentially what we did with the max A, is that we fixed the advantage to a baseline. Likewise, doing this average advantage, subtracting the average advantage from whatever is the arbitrary advantage function I am learning, allows me to ground the advantage function. And now this V and this A are perfectly identifiable. So now there is a specific meaning for the V and specific meaning for the A, and I kind of approximately recover that, right. And so this is my new Q function. If you notice, I have been putting a lot of parameters within the Q function and also within the value function and the advantage function. So this is where the full thing of the deep learning piece comes in, right. So I am going to have a value network, right. This is parameterized by beta, right. I am going to have an advantage network, right, that is parameterized by alpha, and I am going to have a common feature, right, feature learning part of my network, which will be parameterized by theta. So I have theta, which is my features, beta, which is the value function, alpha, which is the advantage function, right. And this is the fixed aggregation layer, right. Mathematically it should have been just a simple sum, but the sum does not work because I am not computing the V and A directly, right. I am just using it as a back propagated from the Q function, right. So this aggregation layer will implement this function, right. This is basically implemented in this aggregation layer, okay, this function. So it will take the V and then it will take the average, it will add all of these things, take the average of this, subtract it from the actual advantage of that particular action, and then give that as the output here, okay. Makes sense? So now this will give me an array of Q values, right. Remember, V plus A gives me a Q array of Q values, and from here I can choose an action according to whatever I want, right. So according to epsilon greedy or softmax or whatever, I can choose actions from here, and then I can find the the DQN error function and then back propagate through this, right. And of course, I might want to do like a target networks and all of these replay buffer, everything can come into play here. But the point is, I'll have a single set of feature learning pipeline. So this is what makes the feature learning more robust also here, because I am putting in the value error as well as the advantage pathway, right. So there are two pathways that are coming in to kind of make the features more robust. It's kind of like an auxiliary loss based learning approach. So this is the basic idea behind dueling DQN, and of course you can do dueling double DQN if you want, and that just combines the ideas that we have talked about so far and makes the whole thing more robust, right. Right. So the last piece that I wanted to talk about today is a slight improvement on SARSA. right. If you will remember, right, the SARSA was basically using whatever action you take next, right. So, you start with ST comma AT, right, and then you go to ST plus 1, right, and you get RT plus 1 along the way, right, and right. Q learning would have just used this, right, and then did a max over AT plus 1, right, while SARSA will actually look at AT plus 1 as well and then do the whole update. So, that is what we had, right. So, the problem with this is that of course, doing the max also there is a problem, but you know it's kind of more stable, right. Doing a max is more stable, right. But this AT plus 1 introduces a significant amount of variance, because when you're initially doing exploration, right. So, I mean, or whenever during the initial stages of the learning, the action that you take here will change wildly, right. Sometimes an action becomes better, sometimes you know, because you're doing exploration, you're adding a significant amount of noise to what AT plus 1 is, right. While when you're doing max over all possible next actions, you're kind of you know, slowing down how quickly the next action changes, right. But when you're actually doing this, your epsilon greedy or softmax, whatever you're using, is going to cause you to change your action rather rapidly, right. So, this can introduce a variance and that slow down convergence, right. So, that is a problem. Right. So, one thing that we can do is you know, slightly expand SARSA and do an update which is called expected SARSA. Right. So, what is the meaning of expected SARSA? Expected SARSA essentially, instead of looking at, I mean, so we are in some sense doing expected SARSA, right, already. So, the only difference is this expectation we approximated by just one sample, right. Right. These are random variables, right. When we are doing the normal update, we are approximating the expectation by taking only one sample, right. Now, what we can do, right, we do not know the true transition probabilities, right, we do not know the true reward distribution, none of these we know. But what do we know? We know for sure what is the policy that we are following, right, at that instance, right. So, we know the policy that we are following at time t, right. So, I know the policy that we are following at time t, right, when you are doing SARSA. Why? Because that is epsilon greedy softmax. Basically, whatever is the current Q values, I do epsilon greedy with respect to that, or the softmax with respect to that, I can construct my pi. Right. Therefore, I do not have to take a approximation of this expectation, right. I do not have to take an approximation of this expectation, I can actually take the real expected value, right. So, the real expected value will be summation over all A, right, pi of A given ST plus 1 into Q of ST plus 1 comma A. So, I do not have to worry about what is the actual action I took, I can take the expectation over all possible actions I can take, right. So, because this expectation is reducing the variance, right, now I am not really worried about the actual action, all Q values will figure into my update, right. This reduces the variance and increases the speed of learning, potentially increases the speed of learning. I can always come up with examples where this learns faster, and maybe somebody can come up with an example where this learns slower, but the point is this gives you an option to converge faster, okay. So, now, so this is basically how you would do this, right. So, you first compute this expectation, which is the value function really, value function of S prime, and then you do expected SARSA with these expressions, right. Good. So, now here is a question, is expected SARSA on policy or off policy? We said Q learning is off policy because we ignore what is the actual action you took and you did the max over all possible next action, right. Now, again in expected SARSA, I am ignoring the action I took and I am taking the expectation over all actions, right. So, is expected SARSA on policy or off policy? Okay, it is on policy. Why? because even though I am ignoring the actual action I took, right, but the expectation I am taking is with respect to the pi that I have currently. So, I am learning the value function corresponding to my behavior policy, because I am using that pi to take the expectation. And therefore, the whole thing is essentially still an on policy algorithm and still SARSA, because I am looking at the next action. It is just that I am looking at the distribution of the next action as opposed to looking at a sample from that distribution. Therefore, this is still an on policy algorithm. So, this is called expected SARSA. Right. So, here are some of the papers from which we talked about these things. Right.